All right, this is now recording. This is week 2 tutorial. So monolithic and compound pressure vessels. I want to start by just having a quick recap of what we did in the 2 lectures. So we basically derived Lamè's equations using the equilibrium condition that we derived from n infinitesimal, the compatibility relationship or the strain displacement relationship, and the constitutive relationships. So we baked all together into this differential equation that is called Lamè's differential equation. Now see, this U as defined was the U, as you can see here, is the radial displacement of one fiber of material. So every fiber of material, so every arc here has its own U associated. So this U is a function of the radius. Since at every radial line, at every radial coordinate, you have a different fiber, each of these fibers moves in a certain way that according to this differential equation. So if you solve this differential equation, you get that the radial displacement looks like this. Again, and if you substitute this back into here and into here, you can find this radial stress distribution and the hoop stress distribution. And they look like this, where C1 and C2 get baked into A and B together with the material properties. As you can see, sigma theta is A plus B divided by R squared, and sigma R is A minus B divided by R squared. So they depend on R. So this is not times R, this is sigma theta function of R, sigma R function of R. So whatever number you put here, you should also put here. And since A and B should be known quantities from the boundary conditions we have here, you find the distribution exactly as we did here. The distributions, they look like this generally. See, this is what we did. What I showed you last time when you have a monolithic pressure vessel and you change what's going on here. It's MATLAB. There we go. So if you change the distribution here, you see that it changes. This computer is a bit slow. Yeah, they look like these when you have only internal pressure. If you have external pressure as well, of course, you have to make your calculations, because at some point they might be constant or they might go, well, they might invert their curvature. Come on, there you go. Yeah. What's going on? How many tutorial sheets are there for this week? There are 2. So we have tutorial sheet A, this one, Lamè's equation tutorial sheet, and we have tutorial sheet B. We are not going to go through all questions. We'll solve 2 questions from tutorial A, 2 questions from tutorial B, and then I'll give you some hints on which tutorial questions will help you in the coursework as well. Because there are some questions here that are quite, I'd say not similar, but they contain elements that you also find in the coursework. Don't worry. All right, so axial stress, of course, this sigma z depends on whether it is open ends or closed ends, because if you have cups, of course, the internal pressure will tend to elongate the container, and that means it will feel some stress. Axial stress, it's a tensile stress. Well, you can just find this very easy by just doing this sum of forces equal to 0. Remember, forces are pressure times area. So this stress is also a pressure. So by just looking at this diagram, balance of forces, you'll find that sigma z is constant in the sense that it doesn't depend on the fiber. What's this? It doesn't depend on which fiber you are considering. So whatever arrow sigma z is on this green surface will be constant. So it doesn't depend as sigma theta and sigma r. See, sigma theta is larger at this fiber and smaller at this fiber, whereas sigma z is constant over the entire green area. All right, we also found that for shafts, solid shafts, so no containers, B of the Lamè's equation is equal to 0. So this gives us a very basic description for the, it's inaccurate, but it's very easy description for the state of stress of a shaft, which is always in compression. Sigma hoop, sigma radial is always equal to minus the external pressure, of course. And then we discussed what happens if we have a contact pressure or if we have some combined compound pressure vessels. Okay, so remember, we have a contact pressure here, so we have two of these distributions, but one of them, well, the two of them are sport a jump in the hoop stress and a kink in the radial stress. So this is how it must be. Okay, so there you go. This is something like this. Let's say if you have no internal pressure and no external pressure, but you have some interference, this is what's going on. So you have that the radial stress goes from 0 to the contact minus the contact pressure, and then it goes back to 0. And then the inner layer feels compressive hoop stress, and the outer layer, of course, feels tensile hoop stress, as because the contact interface is an external pressure for the inner layer and an internal pressure for the outer layer. That's how it works. So you can study this independently, individually. There are many ways, but you can always resort to the Lamez equations anyway. You find your A's and B's. All right. So let's start by solving question 1 of the Lamez equations tutorial sheet. Very easy. So this is just a warming up. So we have the cylinder of a hydraulic ram, which is a 254 millimeter internal diameter and 50 millimeters thick. Find the maximum hoop stress in the material and the radial. So we want to find the maximum hoop stress in the material. Now this is a pressure vessel under the influence of internal pressure only. So we know that under these conditions, the internal pressure only, the largest hoop stress, see, must be at the inner face. That's how it works. But we also want to find the radial and hoop stress of both stresses at a point in the barrel, which is 19 millimeters from the inner surface. Okay, so it's just a point for which I am interested to see what's the state of stress at that point, and that point lies 19 millimeters away in the radial direction from the inner surface. We know that the pressure inside is 9.24 megapascal, so it is megapascal, meganewton per meter squared. So this is the formula sheet I just used, I just reported on the paper. And I'll give you 1 minute to copy the data that we have so far. So we want to find sigma r. So what's going on here is that we have a 127 millimeters radius. So we have a diameter of 254, but of course the radius is 157. We have a 50 millimeters thickness here, as you can see. We have an internal pressure PI of 9.24 megapascal applied all inside at 127 radius. And we want to find the state of stress at this point P here, which lies 19 millimeters away from 127. So this lies at the radius of P is 146 millimeters. So how do you solve this? This is very easy. Oh, I forgot. We also want to find sigma theta max, which is of course sigma theta at the inner radius. All right, how do we solve this? Very briefly. So remember Lamez equations. So let me copy these ones. And so I have that Lamez boundary conditions what do we know about this cylinder here? So we need two boundary conditions. We have A and B, which are our two unknowns in the Lamés equations. We need two boundary conditions. Well, the things that we know are that at the inner layer, so this fiber at 127 millimeters of radius is under the influence of PI, and the outer fiber, this one here, is under the influence of no pressure, so it's unloaded. Therefore, we can say that the radial stress at 127 millimeters equals minus PI. And the radial stress at 304 millimeters is 0. Now we can turn this using Lamés equations. We can turn these boundary conditions in A minus B divided by 127 squared equals minus 9.24, and A minus B over 304 squared equals 0. Actually, agree with me that these are both minus A minus B and A minus B because they are both radial stress. So we are just using one of these equations, this one. And this is one cause of the common mistakes that students generally make, is they think they have to use both equations for both boundary conditions. It doesn't matter, because sometimes you have information on just one, but you need two equations. You can even use the same as long as it's as long as it refers to a different condition, or a different, in this case, a different fiber of material. So how do we solve this one? We have equation 1, we have equation 2. So I can do equation 1 minus equation 2, and I get minus B over 127 squared plus B divided by 304 squared equals minus 9.24. You agree with me? Let me check the chat. 304. Sorry, why 304? Oh, yes. Yeah. 304 is because I'm looking at this fiber here. So this fiber here lies at 127 plus 50. So 120. So yeah, no, you're right. 127 plus 50. Thank you. So this was 127 plus 50 is 177. Thank you for spotting that. This is 170. See, it's very easy to make mistakes, no? With radii and diameters. So this radius here is 177. So that means that this is 177 and this is 177. All right. Now, how do we solve this? Well, you can solve this easily, but I will use Wolfram alpha because it's easier. I'll say that x divided by 120, sorry, minus x. Well, let's start with this one. So x divided by 177 squared minus x divided by 127 squared equals minus 9.24. This gives me did I do this correctly? Yes. Yes, looks correct. So this gives me x 307,000. So this x means b. So this, if you solve this with b, you get b equals, let me copy this one, 307,173. And now that you know this, you can find a, and just easily made. So you can x minus. I'm going to substitute b into equation 1. So I'm going to say that x minus 370,173 divided by 127 squared equals minus 9.24. So this is equation 1, where my unknown is now A. I find that A equals 9.80, 9.804. I find that A equals 9.804. Okay, there you go. Now that we know A and B, we go back into the Lamez equation to find the distributions. Now we use Lamez equations one more time. Also, let me do this. Let me draw the actual distribution. Put this. So let's say I have sigma r and sigma theta. Remember, these are megapascal and these are millimeters, the radius. And so I have that this is the initial radius. And this is the final radius, the outer radius. So I can find out quite easily that the distribution looks like this. And looks like this. You see, I am making sure that this line reaches 0. I don't know how much these numbers are. Well, I know that this one must be minus 9.224. So this one is minus 9. Or just let me. Minus 9.24. And what I want to find is, remember, RP. So this number here is 127. This number here is 177. RP is, let's say it's this one here. Which we said is 146. And so what we want to find is this value here and this value here. So this is sigma theta at 146. And this is sigma r at 146. Okay. Well, this is the distribution, but of course, this comes from the Lamez equations. So let me write them again. Sigma theta is of r is a plus b, where now a and b are these numbers here. So I'm not going to draw the numbers again. And this is a minus b over r squared. Okay, so let's use Wolfram alpha again to find what is the value. So a plus b, 9.804 plus b. B is 307,173 divided by rx squared. Yeah, that's better. This one. Let's see. This is how it looks like from minus infinity to plus infinity, but we are only interested in this where x is, so the inner phase is 127. 127. This number is 28.84. This is what we want to find. This is, remember, sigma max, sigma theta max, which is 28.84. Let's say 28.8 megapascals. sigma theta at 146, which are the other two that we want to find. This is 24.21, which of course is smaller. This is 24.21. Sigma r is very easily at the same thing. I just have to use a minus here. Minus 4.6. As you can see, it's greater than minus 9.24, which we know it must be. Okay, and just for completeness, I also want to know what's going on here. So how much is this one? How much is the external hoop stress? So let's find. Very easy, again, very easily. So the hoop stress, I mean, I want a plus sign, and I want it at 177. So this is 19.60, 19.6. This one here. Okay, now we have complete information. We have answered our questions. The questions are what are sigma r and sigma theta at RP, which are these values here. What is sigma theta max, which of course occurs here at the inner phase, which is 228.8. There we go, done. Any questions on this? You can see quite easy. Chat, yeah, chat senti. Questions? No questions? No questions. So let's do question number 2. Again, very briefly. We want to determine the radial and hoop stresses at all points. Now, in this case, when I ask for the radial and hoop stresses at all points, I mean draw the distribution. In a thick-walled cylinder of internal and external radii, these ones and this one, when acted by internal and external pressures of 124 megapascal internally and 46 megapascal externally. Does this mean this gets larger or smaller? What do you think? Overall, the diameters. Can you tell? I mean, if the pressure is only inside, the diameters are getting larger. Although the internal diameter moves more than the external one, so it still results in a compression of the material all around. If there is only external pressure, it gets smaller overall, but again, the outer phase moves more than the inner phase, so still results in a compression of material. So can you tell what's going on here? Remember what I told you last time. It's non-trivial, because what happens is that if you have internal and external pressure, it depends on the geometry. Let's say I have 60 and 60 here. So for the same internal and external pressure, the deformation still goes inside. Okay? So it still gets shorter. That's because, again, it's the forces that count, not the pressures. So since the pressures are the same, but they are distributed over, well, the external one is distributed over a larger area, so then it dominates over the internal one, which is only distributed on a smaller surface area. All right. Show by means of a diagram how each, so let me check the chat. Only 27 people. What? What do you mean only? What? I don't get it, Lucas. Show by means of a diagram how each stress varies over the thickness. So that means just draw the distribution. Again, if you didn't have MATLAB or anything, you should draw this by hand, which is very hard to draw a mostly hyperbolic-like distribution by hand. So it is suggested that you calculate 4 points and then you join them up. Okay? This is piecewise linear. It's not an hyperbolic, but it would be quite. This is just how it does, how Excel does it. So when you want to plot anything in Excel, if you give Excel 2 points, it will plot a straight line. If you give Excel 4 points, it will plot 3 straight lines in between them. So you need many points in order to make it look like it's a curve. Okay, so remember this when you do your coursework. If you plot things in Excel, Excel joins it by straight lines. Don't let Excel do any smoothing for you, because Excel, I believe now in the latest years, the default diagrams are automatically smoothed over. So if you add a smoothness to your straight lines, you might find there are minima and maxima where they should not be. Okay, and this is a mistake. So if you do that, I will pick that up as a mistake. Okay, not necessarily a conceptual mistake, but it is a mistake that you didn't recognize that this is an issue. Okay, I don't know if this makes sense. All right. MATLAB doesn't have this issue. So if you do this in MATLAB, it's fine, but Excel, since it's made for accounting, for accountants, it's not for engineers, really, Excel. You can use it however you want, but it's generally made for other people that like these nice curved lines. We don't like nice curved lines. We like reality as it is. So if you need 4 straight lines, just draw 4 straight lines. 4 straight lines are better than whatever Excel comes up with the smoothness function. Okay. All right, so let's solve this one very briefly again. So question 2, and I'm going to copy this one. Let's say here. We now have an external pressure as well, so I'm going to do this one here. PO. I don't care about these anymore. I have other things to care about, which are the 76 and 152. So this is 76. This is not there, this is not there. And this one is 152. What else? 124 megapascal and 46 megapascal. So 120. I forgot it already. 124, 46. PI is 124 megapascals. And PO is 46 megapascals. Let me check one more time, just to make sure. Yes, 24, 76, 152. Yes. All right, we want to find the distribution at 76, 100, 125, and 152. So let me write this down otherwise. So 76, 100, 125, and 152. Okay, again, guys, so this is just very easy. So I'm going to do this very, very briefly. So I'm saying Lamé's boundary conditions. What are the boundary conditions here? Help me out. Sigma theta or sigma r? Sigma theta or sigma r? Yeah, sigma r, where? Inside. Let's start inside. Sigma r of 76 equals, come on, minus 124, correct? What's the other one? Sigma r or theta? Sigma r again. At 152 equals 46. minus 46. Always negative. The pressure is positive, the stress is negative. The stress is compressive in nature, so it sports a negative number. And then we just use Lemay's equation one more time. And we are going to use the same A minus B over 76 squared equals minus 124, and A minus B over 152 squared equals minus 46. And now I'm going to solve this directly with Wolfram Alpha, and I'll show you how you do this in Wolfram Alpha. You can do this with MATLAB as well. MATLAB has a symbolic solver. I'm not very good at using it, but there is a symbolic solver in MATLAB as well. So if you want to find these, I mean, if you want to experiment with MATLAB, please do so. So this is A plus B. Sorry, minus B, because we're looking at radial stress over 76 squared equals minus 124. So this is my first equation. And then my second equation is exactly the same, but I have 152 and minus 46. And if you do this, say solve this for A and B. Yeah, so it says solve these two equations for A and B. So it gives you a solution of A is minus 20 and B is 600,704. If you have different units, so you should have consistent units among the equations, okay? But if you have different units than Newton and megapascals, these numbers might vary wildly. Okay, so you see B is 600,704 because I'm using megapascal. If you're using Pascal, this may be order of magnitudes different. So don't be scared, just keep using consistent units. So if I solve this, I get A minus 20 and B 600,704. I'm going to say solve. No. So as you can see, it's very easy by just using boundary conditions to find A and B. Now that we have A and B, yes.
In the exam, do you want workings out for how we solve for A and B, or would you just be happy to see what A and B?
This will not be in the exam, but yes, I mean, I want in the exam, whenever you do calculations, I want you to at least write the first few steps of the calculations, and then you can copy the final result from MATLAB or from Alpha, whatever. Okay. So I want you to show me that you know what you're doing, basically. Okay? So because if you just write the boundary conditions and then the solutions A and B, you're missing a fundamental step. Now what I've done here is perfectly acceptable. Okay, so you just say, now that you have said this is equation 1, this is equation 2, I solve it. Because we know how to solve systems of equations. Okay? And at least I hope that at this point, you know how to solve two equations in two unknowns. All right, so that's good. And again, so this topic is not at the exam. This is entirely coursework. So this does not apply in this particular case. What I was doing here, oh yes, I wanted to actually show on Wolfram Alpha the distributions. So now that I know what are A and B, let me plot these two distributions, minus 20 plus 600,704 divided by x squared, and exactly the same, but with a negative sign, for x in the internal radius is 76, the external radius is 152. Let me see if this works. This might be nice. Yeah, there you go. So it's quite nice. You can just copy and paste this wherever you want. And so this looks, can we actually do? No, you probably need. No, there is no data tooltip. You can do this in MATLAB though. Let's do this in MATLAB. So I'll show you how to do this in MATLAB quite quickly. So you want to plot. First of all, let's define R as a vector of 76 to 152. Let me clear. So I'm going to say that R is so if I do this, my vector is 76, 77, 78, 79. So it's 1 point each. Let's say I want it a bit finer. So instead of doing in steps of 1, I'll go in steps of 0.1. So this creates a row vector, which I don't want. I want a column vector. This creates a column vector of from 76 to 152 in steps of 0.1. So it's 761 values. And now I have my A, which is minus 20. And now I have my B, which is 600,704. And now I can plot sigma R, which is sigma theta, which is A plus B divided by R squared. Of course, I can't divide a number by a vector, but if you use dot divide, this is an element by element operation. Okay, so instead of dividing the number B by the vector R, it divides the number B by each element of the vector R, which is an operation that you can do. And of course, since plotting works like this, so R is the x coordinate on the abscissa, and this is the ordinate. This is the vertical axis. If you do this, sorry, I screwed up. Oh yes, also this one, this power, you can't have a vector squared, but you can square every element of the vector. So it's the same thing. What did I do? There you go. It's fine. Let's do this. And this is how it looks like. Nice. Now here on MATLAB, you can actually check the data tips. So you go and do data tip. Oh, we can do this already. Yes. If you plot here, so you can go around and chase the points that you need. This is not the behavior I want. I want to delete all data tips. Is there a way to like this? No. Can you move this around? Move the pointer. Oh, there you go, like this. So you can just go and chase your values that you want. I can do this. Well, let me do this for sigma theta equals A plus B divided by R squared. This is capital A. And square must be like this. And if I do sigma R A minus B divided by R squared, I get this. So I can plot now this and sigma R sigma theta, R sigma R. Sigma R. Did I called it sigma T. I called it sigma instead of sigma R. Oh, sigma R equals sigma T, clear sigma T. There you go. And now let's do this again. Second? The screen's gone again. Oh, just a second, guys. You just need to nudge this a little bit. You see? Nice. And this is exactly what we were expecting. So that's good. So this goes from 75 to 152. Yeah, 152. And you can find all the values you want on these, on this one or on this one. Check the chat. When are my theta sessions? So I don't have a scheduled theta sessions, but if you send me an email, I will arrange one. Okay, so it's I am bookable. You can book me. Okay, so just send me an email and we'll arrange some time to meet. Yeah, because I have too many things going on at the same time. I can't have a fixed theta hour. All right. So guys, question: Do you like this thing which I solve these questions in MATLAB as well in Wolfram, or do you want me to just do tutorial, as many tutorial questions as possible? Is this okay? Can I ask online as well? There's 28 of you. So how do you like this? Do you like it a bit more relaxed? Okay. Okay, I like seeing the MATLAB as well. Thank you, Joe. All right, so let's keep it, because I mean the solutions to the tutorial questions are already released. Okay, so I think there is a little value of me just repeating the same thing in a nicer way. There is a bit more value if I showed you how to do the same things in other ways, especially if this might help with the coursework. Because this is how you plot your coursework plots. Okay, make sure. MATLAB, please. Feels essential. Yes, it is essential, especially if you have to work anywhere. I think that there was a study a couple of years ago, possibly, say that MATLAB was one of the most common softwares that you'll find in industry, which is, of course, it's a mathematical software. So yeah, MATLAB skills are quite critical for engineers these days. All right, now instead of solving, since we have 15 more minutes, I don't want to solve question 4 of this one, but I'll give you some starting points, because it is also very interesting and not quite related to the coursework as such, but it shows you another way, another kind of boundary conditions that we haven't found yet, which is a displacement boundary condition. So in this question 4, we have, of course, we have a geometry and internal pressure only, but see the sleeve, so the outside surface is hooped so that the change in external diameter is 0. So what I'm saying is that if you look at this, let me do question 4. So for question 4, I'll give you the idea only, no calculations. So question 4 doesn't have an external pressure. You know the geometry, you know that is, you know, there is an internal pressure, but what you don't know, well, sorry, the other thing that you know is the fact that this outside surface that I'm trying to select and put in red, this red surface here is constrained. It's fixedly supported. It's affixed to a wall. So it's like this cylinder here is encased in some sort of wall. Okay, so it can't expand. So the outer surface can't expand. So what kind of boundary condition is that? How do you work out the boundary condition on that? So what we want is that the internal pressure is whatever it is, but we have an external pressure. Okay, so the fact that it's pushing against the wall means that the wall is pushing against the outer surface. But you don't know how much is that external pressure. You know that is an external pressure such that the displacement of the outer surface is 0. So what I'm saying is that here, U of the external face u of the external radius is 0. So that's the outer boundary condition. And now let's recall what is u. So let me copy this one. So that means that if you go in the Lamé's boundary conditions, you get that the sigma r at the inner face is minus pi, as usual, and u of re at the external face equals 0. So this is another kind of boundary conditions that you might find. And so that this becomes, so this equation here, so the top equation, of course, is a minus b, whatever, whatever. The top equation is a minus b over ri squared equals minus pi. But the bottom equation, you have to resort to this one. And this one contains a plus b over r squared and a minus b over r squared. And sigma z is needed, if needed. Let me check if there is a sigma z here. It's also a sleeve. So it's only a sleeve. A sleeve means that there is no caps. It's like a sleeve. There are no caps. That means that sigma z is 0. So sleeve, let me write it down here, sleeve sigma z equals 0. And so that gives me re over e times a plus b over re squared minus ni times a minus b over re squared plus 0, of course, because this is sigma z is 0. And that's equal to 0. See, let's count the unknowns. A is my first unknown and b is my second unknown, and they are also here. So this is still two equations into unknowns. It's only harder. Okay? It's only more complicated to solve, but it doesn't change anything because re is a number. These are all numbers. E is a number, E is a number. So you only have to find A and B. Okay, that's good. So I'll give you 5 minutes break, and then we'll start with the other tutorial sheet. Okay, yes, 4 p.m. Hamza is fine. If you want to leave earlier, anyway, it's recorded anyway, so just leave. It's okay. You can catch up later. I mean, it's for this week only, so that's fine, right? I see the equation based on the start. Yes, this one. It's what you will find in the lectures as well. Okay, so it's nothing new. I'm not that you're here. I know that some of you have group project meetings on and so forth, but make sure that for the next weeks you don't have them in the tutorial time. I mean, you have only this one as exam, so try to attend all the sessions of 326MA, okay, and 340. Are these client meetings that you're doing now? Are you doing client meetings now? Yes. Okay. So yeah, that's fine because you have to make sure that the client is happy with the time as well. So yeah, of course, that's okay. Yeah. Yeah. Yep. Of course.
So you said half the same amount of pressure outside and inside. What people majority outside?
Yep. Because the outer pressure is applied over a larger area, and so the total force is greater than the total force inside. Yeah, exactly. No, it's force is P times area. P is F over area. Force is P times area. Okay, it's fine.
That's the number of windows. Remove it from the side of the house. Easy. And then you find the U, which is the equinox. And then you
What do you call the Greek symbol for Poisson ratio? So we engineers call it ni. Greek people call it nu. I don't know why. That's how it works. Ni, like ni. Is it no? Is it not true? Ni as well? Really? No, it's the other way around then. Sorry. So it's ni for Greek people and nu for engineers. I always called it ni, but it should be, engineers call it nu and mu. Also the mu symbol here, like this one, this symbol here. Like the friction coefficient mu, it's called mi in Greek. I have no clue why. So if you can find out, then it would be a nice anecdote to tell my first year students. Yeah, I got this. I got this argument with other colleagues as well, Greek colleagues.
I didn't think so.
How many do you have? I got that. I never used one. Why did I not find
I don't know if she's like the main.
Who cares about your exam? To be fair, if I saw 6 and 7, I used to 6. It's pretty good. Good problem. So you put a you split I thought you would get it. Yeah, you said matter of fact. Raphael, do I have it? Alright, here we are, Raphael. Ooh, you're good at Microsoft. So you speak Alemán, which is English.
Okay, guys, let's resume. All right, so let's solve question 4 of tutorial sheet B. So we have a compound cylinder. So compound cylinder now, we have two, remember you have the core and the sleeve, or the internal layer and the external layer, inner layer, outer layer, however you want to call it. These ones we have complete geometric information as well. Okay, so we know that this one, let me call it R inner. This one, I'll call it R contact, RC. and the outer one, I'll call it RE. Compound cylinder formed by shrinking a tube of 200 millimeter outside diameter and 150 millimeters. So let me copy this information first. So outside diameter, so DE onto, so the larger one is DE is 200 millimeters. DI, so DC is 150 millimeters. DI is 100 millimeters. Now, owing to shrinkage, the radial stress at the common surface is 20 megapascal. What does it mean? That the radial stress is 20 megapascal. And I have to argue that this question also makes a small mistake, because the radial stress must be minus 20 megapascal, because it's a compressive stress for both materials. Even if you're looking at the inside or the outside, they're both. So since the stress goes like this, it's compressive for the inner layer, but compressive for the outer layer as well. So the stress, radial stress, must be minus 20, rather than 20. See. But what does it mean? What is 20 megapascal? That's the contact pressure. So whatever contact pressure PC you have, that is 20 megapascal. What I'm saying is that if you go here, there is a contact pressure that is applied to both sides. You don't see it, sorry. There you go. That's very tiny. But what I'm saying is that it is applied on both sides, so that if you take both of them, you don't see the pressure. But if you do the free body diagram of each layer, you see the pressure. Okay, one going in one direction and the other going in the opposite direction, because it's an internal force. If the cylinder is now subjected to an internal pressure of 100 megapascal, so we also have an internal pressure here of 100 megapascal, PI. PI is 100 megapascals. Determine the magnitude and the position of the maximum hoop stress. Okay, so let's crack this down. We want to find sigma theta max, and also R at which sigma theta is max. Because see, what happens now is that we can have something like this. So we don't have an external pressure, we do have an internal pressure. So it looks like this. So let me, let's say we have something like this, an internal pressure. You see, we can either have this condition here where the largest hoop stress is at the interface, so at the contact radius, or the other way around, we might have that the larger stress is at the inner face. It can never be at the outer face. But in this case, we have to check if it's at the inner face or the interface, depending on, see, this interference dictates the contact pressure. So this means that by increasing this, we change the position of the larger stress. This means we have to investigate what's going on. So now I'm going to solve this via superposition. And by superposition, I mean, we consider first PC only, so as PI was 0, and then we add the effect of PI. So we study this compound assembly as if PI was 0. Then we study the same compound assembly as if PC was 0, and then we sum all together. That's the idea. So let's use superposition. So using superposition, we study PI equals 0 and PC different from 0 plus a condition for which PI is non-zero and PC is 0. So these are the two conditions that we are solved. This is condition 1. Let's call it status 1. Status 1 and status 2. So by summing these two effects, we get directly, I mean, you can do this in one go, but this will greatly complicate the calculations. Okay, so let's do this also because it's nice to see what happens when you shrink fit the outer layer onto the inner layer first without having this in operation yet. So how do we solve this? Well, first of all, let's check that. Let me check what else we have here. Okay, no, that's it. Just it says here it's at the inside of the outer tube. Okay, so let's solve this by saying status 1. PI equals 0. PC is non-zero. Let me do this for the core and the sleeve. And so I'll just copy this one. And I will have this one here. This and this one here. Again with this. No, with this. Okay, so we have core and sleeve. Don't need anything else. This smaller as well, because I don't need all this space. This smaller as well. Okay, for the core, we have an external pressure of PC. And for the sleeve, we have an internal pressure of PC. So we know that PC is 20 megapascal. So let's solve this by using Lame's equations. Boundary conditions. Boundary conditions tell me that this is sigma r at the inner face equals 0, because remember PI is 0, so we don't have PI in this case. And sigma r at the interface is minus PC, which is minus 20. I'm not using numbers yet. Okay, I'm just saying, let's do this. And BCs here are sigma r at the interface is of course minus PC, and sigma r at the external face is 0. So if you solve this, you can find A and B for the core and A and B for the sleeve. So you'll find A for the core, A1, B1. So let me write these equations here in terms of A1 and B1. apologies, when I'm very uncomfortable writing on the left-hand side because I'm left-handed. So my hand just drops over the thing. So I'll draw them here and then I'll move them on the left-hand side. Okay, cheers, sorry. So this would be A1 minus B1 over Ri squared equals 0. And A1 minus B1 RC squared equals minus BC. These ones go here. For these ones, for these other ones instead, we have A2 minus B2 over RC squared equals minus BC, and A2 minus B2 over RE squared equals 0. Now you can solve these. Let's solve these very quickly with Wolfram alpha. Okay, so I have these already. I just have to go back. There we go. So Ri was, I have diameters here. So let me find the radius. So it's 100, 75, and 50. So this is 100. This is 75. And this is 50. I'm going Wolfram alpha again. So here we are looking at 50 and 75. We're looking at 0 and minus BC, which was minus 20. Check. Minus 20, yes. So this gives A1 and B1 are minus 36. So A1 is minus 36 and B1 is minus 90,000. I mean, this should be easy enough to solve by hand as well. Okay, so I just put here the results. And then for these ones, I have RC. So this is 75 now. Oh, so this equation is the same. So the first equation is A2 minus B2 over RE, which was 100. Is it 100? Yes, 100. And this is the same. So it should be this. So I'm writing the second equation first. A minus B over 100 squared over equals 0. And the first equation is A2 minus B2 over 75 squared. Yes. E equals minus 20. All right. So this is approximate form. So A2 is 25.71. And B2 is 257,143. All right, there you go. So we highlight these ones. So these are the results. And now we can find a distribution. Now, if you plot these distributions here, let me do this in MATLAB. So now we are so good now. So clear A and B. And clear sigma r, sigma theta. R as well, because R is different, of course. Now I need an R that goes from 50 to 75. So R1 goes from 50 with the steps of 0.1, steps of 0.1 to 75. And R2 goes from 75 to 100 with a step of 0.1. Now I want A1 equals minus 36, B1 equals minus 90,000, A2 equals 25.71, B2 equals 257,143, and now I can find sigma R 1 equals A1 minus B1 divided by R squared. I remember I have to use element-wise operators. So this is sigma R1. Oh, of course, I have to use R1. And this is sigma theta 1. And I have to use plus. And now I can plot. Now this, I'm doing this just for the inner shell, of course. And I found sigma theta. So I'm plotting the first part just for the core. If I do R1, sigma R1, sorry, sigma theta 1. And R1, sigma R1, I get this. Okay, so this is just for the core. I have to see what happens for the other one. So I have to find R2, which I already have, and I have to have sigma R2 is A2 minus B2 R2 squared, and sigma T2 is A2 plus B2 over R2 squared. And now I can plot everything again. So this one I plot R1, okay, and then I hold on, and then I plot this one more time, but with the other two. So they retain the same colors. I'm doing this as a trick. You can plot them. You can plot R curve, R curve, R1 curve, R1 curve, R2 curve, R2 curve. But this will give you 4 different colors, which is a bit unwieldy. In this way, I'm retaining the same colors for the theta, for sigma theta, and the same color for sigma. So this is R2, ST2, R2, SR2, and there you go. And no, it changed the colors anyway. Okay, so no, it's fine. Let me just wait until this goes up. Okay. So as you can see, this is the situation. Now, this is the radial stress that goes from 0 at the interface to minus 20 at the outer face, sorry, at the interface, and 0 again at the outer face. And this is negative hoop stress for the core because it's under compression, and positive hoop stress for the sleeve because it's under tension. Okay, let's take this aside and let's solve this. So now you know the distributions. You can say now you know. The distributions. Sigma R of R and sigma theta of R for status 1. Remember, status 1 means no internal pressure. Now, question for you. Do I need, now that I have no contact pressure, because I'm analyzing status 2, do I need to consider the core and the sleeve or not? What happens when the contact pressure is 0? That means you have no interference. But if you have no interference, this means that it's a monolithic shell. Okay, so it's a monolithic cylinder. So instead of doing the same thing of dividing core and sleeve, I'm just taking everything. So I'm just copying this. And I'm saying, okay, PC is 0. So I can study this as a single shell. Instead of doing this thing, I can say, okay, this is just this. Okay, where RC, I don't care. Let me check the chat. Will you scroll up a tiny bit, like here? These are the distributions you're looking for. But of course, you can also find, ideally, see if you have no interference, so no contact pressure. Sorry, no, if you have just interference and no internal pressure, so it's exactly how it looks like in our real case. So this is a generic one, but this is our case, proper case. Okay, so this one, this branch is this branch is this, and the radial stress has this kink. Okay, so that's how you know that is correct. All right, so let me do this now, and this is quite simple. Don't care about this, don't care about this, don't care about this. I don't care about the PC anymore. I only care about PI. PI was 100 megapascal, so PI is 100 megapascals. And now I have Lamés equations again, so boundary conditions. These are sigma r at Ri is minus Pi, and sigma r at Re equals 0. So this means that we need another set of A and B. I'll call this A3 and B3. So A3 minus B3 over Ri squared equals minus Pi. A3 minus B3 over Re squared is 0. And so if you solve these, you get that A3 equals and B3 equals. These numbers are solver. So A minus B, Ri was 50. And that's equal to minus 100. And A minus B over 100 squared is equal to 0. Solve these. Let me check if they look correct. Yes, they look correct. And so if I solve this, is 33.3 for A and 333.3. 33.3 for A. 333,333 for B. And now if I do this in MATLAB means I create A3 and B3. A3 is 3.3 and B3 is 333. Okay. Now I can create sigma R3. Let's call it sigma R internal. So no, let's call it 3. Okay, but we must sum all the contributions. Okay, so make sure that you know what you're doing every time. So SR3 is A3 minus B3. Let me copy just these ones. So SR3 is A3 minus B3. R3, we didn't define R3, and R3 I'm going to define it as R2, R1, and R2. Okay, because I want R3 is over the entire thing. And so if I do this now, 3, A3, B3, R3, that's T3 with a positive sign. And now I can plot everything again. So this is this. Well, at this point, let's plot it. Let's plot everything in blue. So the T1, R2, ST2. And this will be in blue. Sorry, this keyboard, wow. Okay. So this is the first plot in blue. But what we want is, no, we need to sum them in some way. So we need to find their sum. So I can't just sum ST1 with ST3 because ST3 is a 502. So what I need is, let me see, S total, ST total equals ST1 and ST2 side by side plus ST3. This should be correct. Yeah. And the SR total is SR1, SR2 plus SR3. Does this make sense? Okay, so I'm just putting the vectors one, append the two vectors and then sum a longer vector. That's the idea, because ST3 is twice as large as ST1 and ST2. Now, if I plot these ones now, I can plot R3 with ST total and R3 with SR total. What is it? Oh, sorry, let me plot this again. Let's see. This one is exactly what we are expecting if I include an internal pressure. See? If I include an internal pressure, I get this one with a jump, and this is the jump. And I get a king at 75. All right? Good. Any questions? So how much is the stress? 163.98 megapascals. Now that we have A3, B3, let me do this by hand as well. Well, not the calculations by hand, but by hand, how would you find out that sigma theta? Now that you have this, you can find sigma theta. Oh, come on. So sigma theta, now using superposition. So if you sum the two stati, what happens is sigma theta total is sigma theta of status 1 plus sigma theta of status 2, which is equal to A1 plus B1 divided by R squared plus A3 plus B3 divided by R squared if R is smaller than RC. Do you agree? Because if it's smaller than RC, we are using the core stress plus the A3, which is common. So the core stress plus the common stress. Or you use exactly the same thing, but with A2 and B2 here, if R is greater or equal RC. Do you get the idea? And that's where the jump comes from. It's the fact that we have two different definitions for the same function, depending on where you are. You see this sigma theta total equals this piecewise, it's called piecewise function because it's defined in chunks, which, if you remember, it's exactly what we did in first year when we found the internal forces we needed to, since we can't have, say, a bending moment that jumps, we have to study it in segments piecewise. And of course, you have the same description here for sigma r. Just copy this. You have exactly the same for sigma r, but for sigma r, you have negative signs. And now, in order to find where is the largest theta, sorry, where is the largest sigma theta? So where is sigma theta max? Since you know that this is a decreasing function and this is a decreasing function, they must be at the start of the function, because if it's a continuously decreasing function, that means that the maximum value is at the start. But at the start might mean r equal, so since, let me call these 1 and 2, since 1 and 2 are monotonically decreasing functions, the maximum value can lie only at the start. And since we have two branches, it's the start of the first branch or the start of the second branch. All right. So you cannot, so we check. Sigma theta at Ri, and we check if it's greater or smaller than sigma theta at Rc. Because Ri is where the first branch starts and Rc is where the second branch starts. Does this make sense? Any questions? No? See, the mathematics is always the same, but the meanings, you must be rigorous and careful. Do you know what monotonically decreasing means? Decreasing means that, I mean, it goes down. So the following value is always smaller than the value before. And monotonically decreasing means that it's strictly smaller than the value before. So it can't be constant. So a number after, so the second value is always strictly smaller than the first value. The third value is always strictly smaller than the second value, and so on and so forth. So in these branches, there cannot be a constant line anywhere. Okay, so last one, because I'm going to solve this last question here, which is question 5. Question 5, where is it? Here. We have a steel collar is to be shrunk onto a solid steel shaft having an external diameter of 150, whatever. If the maximum stress is in the collar must not exceed 139 megapascal. So where is the largest stress in the collar? Is it at the inner face, at the outer face, in the collar? Because see, we have a shaft and the collar around it. The shaft is under constant stress. We know that, it's easy. The collar feels this. Let's go here. The collar feels this. See, the shaft is always under constant stress, and the collar, the largest stress is always at the interface with the shaft. Okay, it must be. I mean, it can be positive or negative, but the largest one is always there. All right. We need to calculate the radial pressure, so the interference. So the given the interference, we need to calculate the contact pressure. No, it's not given the interference. It needs not to exceed this value here. The difference in diameters before shrinkage. And then here it is proposed to press the collar onto the shaft instead of shrinking it on. So see, instead of doing this heating and then cooling. So if you heat the sleeve, then it gets larger. Then you can fit the shaft in and let it cool to create interference. But you can also do a press fit. So just force the shaft into the sleeve and call it a day. But of course, this means that you have some friction. And it's asking how much force you need, how much press force is required for this press fit to happen. And this is linked with the coursework, because part C of the coursework is asking you. Now, part B of the coursework is asking you to do the same thing that we did in part 4. And part C of the coursework is asking you to calculate this press force as well. So let's do this very briefly again. Very briefly, let me copy this one. What am I doing here? Come on. Of course, here I don't have this one, because this is all shaft. Let's make it smaller. Don't need neither of these. This is R, C. We don't have an internal pressure, but we have a contact pressure, of course. So we do have a contact pressure here, PC. Let me clear this. Let me, so steel collar is DI, so DE 230, and internal diameter, so DC is 150. Maximum stress, so sigma theta max must be smaller than 139 megapascals. So we want to calculate PC, the contact pressure, and delta, the difference in diameter. So we want to calculate 2 delta. Remember, delta was the radial interference. So we want 2 delta, which is the diametral interference. So the difference in diameters. And we also have the length of the collar, L, is 75 millimeters. Coefficient of friction, mu, is me in Greek. 0.2, no units. We also have the material properties, of course, which are E, 201 gigapascals, and Ni, 0.3 Poisson's ratio. All right, I think I have everything. This is what we want, and this is what we have. So, boundary conditions. What are the boundary conditions of this? Well, we know that, let's start from the shaft. Shaft is very easy. Remember, B equals 0. That's the main thing of shafts, that B equals 0, and that means that sigma theta equals sigma r equals A equals minus BC. Easy. That's always the case for shafts. Whereas the collar, and here we have A and B. So let's call this A1 and B1, B1, A1. For the collar, we have how many boundary conditions we have? The external pressure is 0. So we know that sigma r at the external face equals 0. What else? At the inner face, sigma r at the contact radius is minus BC. Let me do this using Lamé equations. So these are the boundary conditions. Lamé equations mean that A2 minus B2 over RE squared equals 0, and A2 minus B2 over RC squared equals minus BC. How many unknowns we have here? 1, 2, and 3. Two equations and 3 unknowns. What's missing? Do you want to add this one? Okay, so we are adding one more unknown and one more equation. So now we have 3 equations and 4 unknowns. So see, it's useless. So let's not add this one because it doesn't give us more information. Yes, it adds one equation, but it adds one unknown. So what's missing? Come on, guys, we don't have much time. 15 minutes left. Second? What? New. No. What's missing is this equation here. Okay. We have to remember that sigma theta max, where is the maximum expected? So this is a bit tricky because it doesn't tell us at which radius this is happening. You must know this. Okay, so this is the sort of thing that might sway you a bit. But what's missing? The third equation that is missing. So let me add it here. So let me put these ones here. The third equation that is missing is that sigma theta at the contact face equals must be 139. Okay, so this is equation 1, this is equation 2, this is equation 3. And this equation corresponds to A2 plus B2 over RC squared equals 139. Okay? And now we have 3 equations and 3 unknowns. And now we can solve this. And I will solve this with Wolfram alpha, of course. Because why not? So I have to add one equation. So this is A minus B over RC. How much is RC? So DC is 150. So RC is 75. And this is equal to 0. A minus B over R. No, this is RE. No, this is RE. So RE is 115. Yes, 230. So let me show you. So this means that RE, so this here, RE is 115. Agreed? 230 diameter, and this means that RC is 75. So let me use these numbers here in the equations. So this is the external pressure. So this is looking at the external radius, RE, and this is 115. And this is the contact one, which is 75, and this minus BC, which I don't know. So let's call this P. And then we have another equation that is A plus B. Copy and paste. Is A plus B divided by 75 squared equals 139 for A and B and P. Let me see if this works. Should work for 3 equations. Yeah, it works. Nice. So approximate form, this gives A. So solving this one. Gives A2 41.47, B2 557, and PC 56 megapascals, 0.042, whatever. Okay, now that we have this information, how do we find, well, this is one thing. We have to find 2 delta. What is delta? Remember this? Let me copy this and this. All the way down, all the way down, all the way down. There you go. I don't need this one. These 2, I'll just make them smaller. Okay, so this is the formula sheet. So the radial displacement, so sigma z is 0. Remember, because it's a sleeve, it's open-ended, so you don't need sigma z. So 2 delta is 2 times U2 minus U1, or U1 in absolute value plus U2 in absolute value. And so this is just equal to, let me do this in blue. It's just equal to, and U, of course, is U of the, this is twice times, let me do this here, 2 times RC over E1 times A1. So this is A2, not A1. Yeah, no, it's A1, and this is the absolute value. A1 plus B1 over RC squared minus Ni times A1 minus B1 over RC squared, close, 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 this, plus this again, this here. I mean, it looks complicated, but it's very easy because these are all numbers now. So there is really nothing to worry about. And these ones are just 2, 2, 2, 2, 2, 2. Okay, so this one. So these are all numbers now. It's very easy to find a diameter interference, which is, how many microns is this? Let me check. So it should be 0.146 millimeters. So 146 micrometers. We have A1. A1 is minus PPC, which is this number, sorry, this number here that we found. B1 is 0. A2 is this number. B2 is this number. E and Ni are these numbers here. And so we have everything. All right. So these are all numbers. We just have to substitute everything. The last part is the most interesting one, which says, what is the press force? Now, I have a situation like this. This is my shaft. This is the shaft. Now, the collar is 75 millimeters long. This distance here is L. Okay. Now, the total friction force that is required, that we need to overcome, is the pressure times this area. You agree? This area is all around. The pressure is all on top. So the pressure is, of course, the contact pressure, PC, which is applied everywhere, which we know is a number. And so I'm saying that the friction force, remember, what is the definition of the friction force? Mu times N. Okay. Mu times N. What is N? The normal force, which is the force that closes the contact. And the force that closes the contact is PC times the contact area. How much is the contact area? Well, it's this circumference here, all around, times the length. So it's 2 pi. 2 pi, the contact radius, times the length. Mu is a number. PC we found. 2 pi are numbers. RC is geometry. L is geometry, which is given. This gives a force of, let me check, 396 kilonewtons. Ta-da! It's not very complicated. You just have to make sure that you know what you. This is first year stuff, just applied in a slightly different way. That is not always obvious, but it helps. Now, for the 340 guys that are with me, I suggest you also look at question 6, because question 6 contains one of the elements for your coursework as well, which is exclusive to your coursework. And it's this, the least temperature difference to allow the outer tube to pass on the inner tube. Now, something that you might have or you might have not encountered during your 3 years are this other material property, which is called alpha, called coefficient of thermal expansion. Do you know about that? So how is that coefficient of thermal expansion defined? Coefficient of thermal expansion. How is this defined? What is it? Alpha. Alpha is a strain divided by a temperature, a jump in temperature. Okay? Which strain? In this case, well, this is expansion, so we're looking at radial strain. So epsilon r. Oh, sorry, you can see it. It's epsilon r. Yeah, sorry. Something wrong with my mic. Okay, I'm not sure about that. Can you hear me? It's my accent, it's not my mic. So this is alpha, is epsilon r over delta t. And remember, what is epsilon r? Epsilon r, you can define it also as the diametral interference over the contact diameter. And so this means that delta t is just diametral interference over alpha DC. This alpha is a material property, and as you can see, has the units of 1/degree. 1 because strains has no unit, and degree because you have delta T at the denominator. I will leave the rest to you to figure out. Okay. Thank you very much, guys. It's 2 minutes to 4. I think we had fun today. If you have any questions, ask me now. I'm going to stop recording. There you go. Bye.